matching algorithms. No, not next, same module it is there. I'll show you the, no need of showing the syllabus. String matching algorithms are there. We have to study majorly 3 string matching algorithms. First one is Knight string matching algorithm. Second one is Knuth-Morris-Pratt. And third one, I think, Boyers-Moore's something is there, I think. Forgot the name. But anyway, these 2 algorithms are there. Knight string matching, which is the basic algorithm. Then Knuth-Morris-Pratt, which is in short called KMP algorithm. So first we will try to understand what is string matching algorithm, where it is used. String matching algorithm is a huge application, like in Microsoft Word and then editor, all Excel. You search text, so you have to find the strings which are matching, right? Writing papers also you try to find the errors using string matching algorithm. So text editing programs frequently used to find all occurrences of a pattern in the text. Typically the text is the document being edited. So in the Notepad, WordPad, everywhere we use this string matching algorithm, okay? So text editing, it is required. String matching algorithm is required in text editing. Okay, so another application of string matching algorithm also we have found little bit in dynamic programming of longest common subsequence. But that is not string matching. Longest common subsequence and this is different. What is the difference? Good. So here it is continuous. I told in that time also it is continuous, but in case of longest common it is not continuous. Okay. So here you will be having a specific pattern. That pattern has to be matched with the text portion of the text. If you get a match, you will say, okay, I get match. How many matches you have? You have to find that. Okay. So basically what happens? So basically you have throughout the chapter will maintain one nomenclature. T, capital T is the text, large text that is given to you of length n, and the pattern that we will be looking at, which is P1 to M. That means the length of the text is n, length of the pattern is M. Always pattern will be less than, but it cannot, it should not be more than n by 2. That is one criteria is there. We will follow that. N, that means you should not have so much big pattern which is you are struggling to find it. Okay, so M should be n by 2. Half the text, maybe the maximum size of the pattern's length. Okay, so normally what happens, this string matching algorithm is not only in terms of strings A, B, C, D up to Z, which is called sigma. You know, theory of computation, when you will learn, you will understand sigma means it is like shown like this. That means you can generate any number of strings using all the characters available. Similarly, it can happen with the binary bits also, like 001, 101, all the combinations of binary bits. So these are called universal set. So if you write here star, these actually represent in terms of A plus B star. That means any number of strings you can create with A, B. Okay? Or if you write A plus Z, let's say A dot Z, that means any number of things you can create, any strings you can create. Universal set it calls. Okay, so this normally represent in terms of sigma all over in theory of computation, in compiler design also these are represented like this. Okay, pattern is the string that you are looking for. I will show you the string that you are looking for in the text, the match you are looking. So here one figure we have, you can see that figure 32.1, we say that the pattern P occurs with shift S. So basically what happens, initially my shift is 0 when so my pattern is here A, B, A, A. So my shift is 0 here, pattern size is here 4. So this is shift 0 will start, okay, shift 0, which you will, every time you just move this pattern, you can consider it as a sliding window. One bits by bit it will move one place at a time. Okay, so if P occurs at the beginning position S plus 1 in the text, so T is nothing but, so here T is not starting from 1, it is starting from S plus 1, because shift we will consider it starts, first shift is 0th shift when initial condition. That's why it is S plus 1 to S plus M. Okay, so here you can see that when we say that S is a valid shift, when the match happens, like in this case match happens, it is a valid shift. So at which position you got valid shift? S equal to 3, because S starts from 0, 1 to 3 you got valid shift, otherwise we call S as the invalid shift. So the string matching problem is a problem of finding valid shift with which A given pattern P occurs in the given text. Okay, Professor, problem statement is clear. So here they have taken this text here and the string they have taken ABA and they have found it. So this is basic, and then these are the algorithms that we will be discussing. First algorithm is Knight string matching, which is the basic algorithm. Then Rabin-Karp string matching algorithm, finite automata, and Knuth-Morris-Pratt. Knuth-Morris-Pratt, in short, it is referred as KMP algorithm. Rabin-Karp is also there, and then these are the algorithms, and these are the time complexity given. That we will discuss while analyzing the algorithm. We will see how this time complexity come. Normally, what do you think? How much time complexity will be there? N into m, n square, you can say, okay? N into m, n square, because you have length of the text is normally m. And what is that we have taken? No. Here, how much you have? N. So this is n. The text is n. I am telling overall, you will see how to reduce, what is the problem, all these things we will see. But normally it will happen like this is the text and this is your pattern. Every day match happens. So two things happen. One thing is that it's like a bubble sort of types of thing for knife string matching algorithm, because first you need one loop here. You need another loop also here. If you think from the layman point, because one loop you need, why? Because first character you took, second character you took, third character, like that things are going on. For the pattern also, even the pattern size is n by 2 maximum. Here also you need a loop to read this each and every character. So maximally 2 loops will be in place, so it will be n square. We will assume that. So that is the thing. So terminology, as I said, sigma star, you might be knowing already. Sigma star, basically whenever you write sigma is basically if you write a plus b, and if you put a star here, that means this a plus b star. If you don't put star, means all the strings, no null strings will be produced here. That means null string means nothing, no string, which normally referred as lambda. Okay. So if you put star here, that this will include null string also. So that means sigma equal to a plus b star. If you put, means lambda a b, all combinations of this thing will come. So sigma star, universal set. And sigma star is nothing but empty string, nothing is there, okay? And then we have string concatenation x plus y, 2 strings you can concatenate. Another interesting thing is that what is the prefix and what is the suffix of a string and how it should be denoted. So let's say we have a string w is a prefix of string x. So w is a prefix. Prefix in the sense, prefix means what? Yeah, let's say a, b, c, d, prefix will be a, prefix will be ab, prefix will be abc, prefix will be abcd. Okay, this is prefix. And then another one is suffix. Suffix will be d, cd, bcd, these are all suffix. So prefix is normally represented with this. So w is a prefix of string x denoted by this if x is wy. For some string y belongs to sigma star. This is the scenario, okay? Note, if w is a prefix x, then size of the w, that means length of the w should be less than equal to or equal to x. That means what? If I have abcd given string, main string, if I want to find a prefix, then abcd itself is a prefix to it. That's why it is less than or equal to. Otherwise, it will be all less than the length. So that's why it is less than equal to, okay? Similarly, we say that, no. Which one? X equal to wy, okay? Wy for some strings. Y is that here it is y. You can consider this as a y. You can consider this as a y, okay? You can consider this as a y, and you can consider this AB as a w. You can consider this as a x. Fine. Your y can be anything. Yeah. Which one? Sigma star, when I write, sigma star is nothing. It's a universal set. It's a universal set which will be containing all the combinations of the characters that will be forming the strings. So if it is a plus b star, sigma star is a plus b star in the sense it will also generate lambda null string and then whatever strings are possible, all combinations. That is sigma star. There is a representation, nothing else. We haven't come back. This is just a simple thing. Which W? X. All are sigma. Sigma star is a universal set. Null string. Sigma star all belong to sigma star. All belong to sigma star. Whichever string taken. Why these fans are not working? Okay. So, madam, this sigma star will be, it is a universal set. Universal set. Okay, which will be having all the letters, anything you can think of, this will be having that. So that is universal set. If you put sigma here, it contains null string also. Null string means no strings. Okay, so this is the scenario. You have some prefix, suffix, all these things we understood. Now there is one lemma. With this lemma, we will not go detail in the mathematics, just visually we will see that if suppose that x, y and z, so here they are using transitive properties. Transitive property, all of you know, if A implies B and B implies C, then A also implies C. This is transitive property. So here what it says, one lemma, simply graphical lemma, no this thing. So if x, y and z are strings such that x is a suffix of z and y is also suffix of z, then if length of x is less than length of y or equal to, then x will be also suffix of y. Okay, otherwise it's a vice versa. If x is greater than y, then y should be suffix of x. So here visually you can say x is a suffix of z, y is also a suffix of z, and x is first case x is less than this, x is greater than y in this case. So right, correct, no? So x less than y. Okay, so you understood this graphically. Transitive property. Okay, this is a suffix of this. This is also a suffix of this. This length is less than this, so this length is less than that. This is also a suffix of this. Transitive property A, B, C. Okay, so you understood this. Now next is the main thing, which is called knife string matching algorithm. Very easy algorithm. What we are doing, knife string matching means we have a string. Just now whatever I said, that is knife string matching algorithm. So n is the length of the text and m is the length of the pattern. So here for loop is there. So every time it checks. So meaning is what? This is the scenario we have. So this is my text T. This is my pattern P. So here checking will happen. So it is first iteration. That means first shift A is compared with A. A is not matching with C. So it will go to the second shift. It will just come below C. A is comparing with C, which is not matching. It will go to the second shift. Okay, so it is matching. Then once it is matching, then it will check second character of the pattern. It will be matched. Third character will, if match happens, then you will write matched. Okay, otherwise again it will go to 3, again mismatch happen. So this algorithm is what? This algorithm is called knife string matching algorithm. It happens like this. So P1 to M equal to PS plus 1 goes to S plus M, and then if pattern matches, it gives. So here basically you have to remember, here also one loop is there actually, right? This is just shown in terms of if else. Here one loop, here another loop. So basically the time complexity will be how much? So procedure knife string matching algorithm takes n minus m plus 1 into m. That means it is almost n square. Because why we are taking n square? Because every time we consider worst case scenario. So if m goes to n by 2, then it is like total things will give us theta of n square. Okay, so this is knife string matching algorithm, which is the most basic algorithm we have. Thomas Koch next. Coleman, everything is from Coleman only. Understood, Professor Thomas H. Coleman. First day I am telling Thomas H. Coleman, every day 2 times. Thomas H. Coleman, I will show today again. Okay, so this is the algorithm, knife based, very easy, knife string matching. Coleman, C-O-R-E-M-E-N. Professor, clear or not? Concept clear or not? Okay, very good. Then you do this. Very easy. Make a table. Easy only, sir. Here you have to show all shifts, okay? Algorithm is there in the book. Why to unnecessary waste time? So you make a table, like that you make a table. This will be easier. Put here all text, start with S0. This is your pattern, okay? Start it. And tell me how many matches are there and how many mismatches are there. You check it from there. Okay, right? What you find? That is also there, and also in the website, control A will check, no? Does that? Programs are there at the back. They use these algorithms. Not this one. This one is easier one. They might be using more complicated. I mean, efficient one. Okay, good. Normally you do that, sir. Okay. Huh? First step also. Zero, zero, zero. Done, ma'am? Yes, ma'am. Yes, sir. The first one is this. So you have to write here mismatch. Then this is shift 1, 0, 0, 0, 1. Pattern found. Matches, right? 0, 0, 0, 1. We got a match here. So here you write pattern found at shift S equal to 1. Then next is 0, 0, 0, 1, which is again mismatch. So you have to complete that. Again you will get a match. Okay, so Rabin and Karp propose a string matching algorithm that performs well in practice and that also generalizes the other algorithms from related problems such as two-dimensional pattern matching. Now, Rabin and Karp string matching algorithm is little bit different than naive string matching algorithm that we have discussed. Okay, so here normally what happens in Rabin-Karp, like naive algorithm, the Rabin-Karp algorithm also slides the pattern one by one. That means you will be having a P, capital P, pattern P. But unlike the naive algorithm, the Rabin-Karp algorithm matches the hash value of the pattern. So here extra component is finding the hash value. So hash value of the pattern it calculates with the hash value of the current substring of text, and if the hash value matches, then only it starts matching the individual character. That means your pattern will be there, it will move one by one, shift-wise it will move like naive algorithm only. But here it will not unnecessarily spend time if the hash value is not matching. That means the text chunk as well as the pattern hash value both has to be matches, and then only it will go further checks. So somehow it will enhance the time complexity of the naive algorithm. So basically in Rabin-Karp algorithm needs to calculate the hash values for the following strings. First thing is the pattern itself. That means you have to calculate the hash value of the pattern and then all possible substrings of the text of length m. So both the cases you have to calculate the hash values. So here only thing is, the interesting thing is that here hashing is happening, some sort of hashing, basic hashing actually, and that hash value we are using to check. Basically first the hash will be checked for the pattern, and then text chunk that the window is moving one by one, right? S equal to 0, S equal to 1. Every time you are moving T1, T2, T3, the text up to Tn it is going, whatever, I don't know, Tm I think. So every time it will check the hash value. If it is matches, then only it will peep inside the things. This is the thing. So we will write the algorithm. Actually in the book the algorithm is little bit tougher, so I found it little bit here easy one. It is not. No. I think it is okay. If not work means I will be in trouble. So Rabin-Karp. Just quickly we'll write the algorithm first. Okay. Two things you have to calculate: hash value. Just in this algorithm, hash value, and we'll try to make it simplified because many things can be discussed in Rabin-Karp. No need actually. We'll just straightforward will move. And the way I am representing the things, you have to do same thing in your exam. Okay. So yeah. So this the step that I will be showing, same way you represent in the exam also. It comes. Okay. So first Rabin-Karp, K-A-R-P, text and pattern both we are passing here. First point number 1 is n equal to p dot length. Second number point is m equal to p dot length. That means both the length you are checking out. Third is hash value, which you can write h, or h you can write h of pattern then equal to n minus m. Hash text hash text, madam, hash text. We will see this. We'll solve one problem. It will be understandable. No problem. 1 plus s plus m. This is the algorithm. That means this algorithm is, you just remember it. Meaning is that every time this line is important, we have to completely read the text, and every time hash pattern is matching with the hash text, then only we'll see the individual character of the pattern to the individual character of the text. That is the meaning. Okay. Write it. Let's say the text is 2, 3. Please come, sir. So here, let's say the pattern P is equal to P1415. This is my pattern. That means you have to match this pattern every time with the text. Okay. How it will happen? You have to calculate the hash value of the pattern and the hash value of the text also, that text chunk. You have to calculate that. Before that, you have to write something. There are some questions are there. So first thing is that to write it. Usually, you have to choose a prime number here. Okay. You have to choose a prime number. Choose Q. That prime number is nothing but Q as a prime number such that P P modulo Q. P is what? This pattern P modulo Q should be P modulo Q should be computed in theta of m time. Okay, I think the size of the pattern is m. Size of the pattern is m. So that you have to know, you have to be a little bit careful that when we will be choosing that Q, which is a prime number, when calculating the hash value of the pattern, this Q we will be choosing, right? Actually, we can choose this Q randomly, any number we can choose, but that Q should not be that much. Q is the Q is another. Q has no relation. Q is the number, prime number that will be used to calculate the hash value of the pattern. That will be used to calculate the hash value of the pattern. Okay, and also hash value of the text. We'll see that. How to choose this? I'll show. Hash value means if you normal hashing means like if you divide 12 by 5. So what is the remainder? That is your hash value. Okay, that is remainder is hash value. That is normally the hash value. Okay. So Q as a prime number you have to choose. Randomly you can choose this number. So sometimes it is asked whether actually you can choose any number, but in the book it is mentioned that Q you have to choose. You can choose randomly also, but I am not sure whether prime number itself you have to choose or if you choose any other number, how it is different and all that I don't know. This is not mentioned, but in the book it is mentioned that Q can be actually prime number, but sometimes it is a little bit confusing algorithm. Sometimes they say that Q also can be a number, but we are just focusing on Q as a prime number and it can be chosen randomly. But while choosing the Q, randomly means that your pattern size is this, you are choosing Q as let's say 2 lakhs. That is not the case. You have to choose Q somewhat small and it can be, so that when you calculate the hash value, it should be happen quickly in your computer. That is an interesting thing. Okay. So this is there and TS, that is the text, that text will be moving, right? T1, T0, T0, T1, T2 like that. It will move like a sliding window, right? So that is TS, but TS is nothing but T0, T1 up to let's say Tn minus n minus m in theta n minus m plus 1. That also you have to notice that this calculation, that slide, the window will be moving one by one, bits by bits, shift wise. It should not also take too much time. Okay, that also you have to look at it. The meaning is that layman point of view, you have to choose Q little bit smaller, should be quickly computable, so that we can find here in T minus 1. I am just telling in between 1. In between 1. Okay, you can take it up to Tm. Whatever is the size, it will go up to this much. P 1 to m in the text, P 1 to n in theta m pre-processing time. Okay, this is some interesting thing that you have to know. Fine. So let us now start directly, and it is very easy actually. Just sometimes it is asked in the exam how to choose Q, what is the relationship, whether Q should always be a prime number or not. So Q should actually not always be a prime number, but we will focus Q as a prime number only, so that the hash value can be created. Hash value of the pattern should be created fast. That is the intention. It should not take too much time. That means they are saying that your pattern and the text should not be too lengthy. Okay, so that it is non-computable. Let us again. So you have written this, so I'll just rub it. So you have pattern. So first you have to directly calculate the hash value. How to calculate? Let's say I am taking Q as 13. In exam, mostly I will be giving you Q, so you don't have to bother what will be the Q value. 7 also you can take, but it will be given. Mostly I will be giving the Q. I'll provide you. Okay. If it is not there, you can take any prime number which is. That's what I'm saying. That is okay. No, I'll mention it. Q. I'll be giving this Q if it comes like that direct question. Otherwise, you take Q of your own choice. Don't take Q so much lengthy, so that it should like divisible. Like this is my pattern. What Q you want to take? Maybe 61 also you can take, no problem. Answer will differ, no issue. You have to see whether matches are happening or not. Okay. But normally in exam Q is given. Q and pattern both will be given. So immediately you have to calculate the hash value. Just divide this thing with 13 and thus yes, sir. $78, right? 78, right? Remainder 7. This is my hash value. When I calculated the hash value of this, okay? Now what you have to do? So first, just let us write this again. This text T 23590231415. Let us take this much. So here you can see that window size is 31415. So you have to take 5 length wala window here. This you have to see, and you have to divide this by 13, and you have to check the hash value. So because here the pattern size is 31415, fifth length pattern is there. So here also I will be taking the text as a 5 of chunk. That means in my shift 0, this first will be checked from the text. So what is the hash value here? Just tell me the hash value. I think 8. Just check it out. It will be 8. Yes. So here also you will be having another table which will simply calculate the hash value 8. Okay. So 8 is not matching with 7. So you have to just simply ignore that. And then next, this you have to take hash value is 9. That also not matching. Then you have to take this hash value is 3. That also not matching. Then you have to take this hash value 11, not matching. Then you have to take this. You divide by 13. Divide by 13, get the remainder. That is your hash value. Okay, 0. So like that, if you go, you will see 0, 1, and then 7. Here one hash value is matching. Which is the window that hash value is matching? This window, 31415. 31415. This window, this hash value is matching here. Once hash value matches, then individual check of the pattern will happen. That means this pattern is actually here, staying here. So this is nothing but 31415. The individual check will happen. Okay. So this 3 will be checked with 3. 1 will be checked with 1. 4 will be checked with 4. 1 will be checked with 1. 5 will be checked with 5. So it is matches. So pattern found. So immediately it will like. So here you have to write that valid match. First the hash value matches, then individual characters are also matches. Okay. The valid match. Okay. Valid match is happening. Now once you have to then go through the whole text. You have to go through the whole text. Then again you have to move the window, and then you have to take this window. 1/4. So basically 1 3 1 4 1 5, and then last one is this is 2. That means if you increase the window size, this is coming like this. 14152. This is your window text. From the text, its hash value is, I think, its hash value is 8. So that also not matching. Then it will further move. Okay. So once you move like this, okay, Professor, clear? Tell me, madam. You have to first you saw that pattern length is 5. So that means every time 5 chunks will be, you will be taking from here 1 2 3 4. This is your first chunk. Then this is your second chunk. Then this is your third chunk. 5 will move. But which text That means which T0, T1, T2, which one is actually matching with your pattern. How to do? First you have to check the hash value. Without hash value you won't even bother about the things. Okay. Here you see, here if you when your control is here, that means 31415, whose hash value is nothing but 7. 31415 you divide by 30. One second. So now if you move, sometimes what happens, there is a catch. Sometimes what happens, this is valid match. Why it is valid match? Because your remainder also matches, hash value also matches, and the text also matches. So this is a perfect match happens, and you have hit. Yeah, now I will show you. Here you have a match here. So this is your hash value array. You can say this one is the hash value array. This is the text. This is your pattern. 31415 is my pattern. See, here 7 is there. Matches happen. This is valid match. Again, when the window is moving from here to this, then this, then this, and then when the window comes here, 67399, your hash value comes again 7. But then when you match this with your individual 31415, that are not matching. So that is called spurious hit. That match is called, that is not matching, so it is not at all helping us. So it is spurious hit. So how many spurious hits are there in the length in the question? It might be asked. You have to find that. The thing is, this algorithm is called, as already we explained in the last class, and I have given the basic idea about Knuth-Morris-Pratt algorithm. So Donald Knuth, who is the pioneer of computer science, you can call. 3 professors, researchers, they have developed this algorithm and very popular. Okay, the algorithm is a little bit out of the box. Like it's not contemporary type. They have thought about the algorithm and they have devised a complex algorithm, you can say. Okay. So how this algorithm works and what is the base of this algorithm? I will try. We have already seen the prefix function and suffix function. Prefix and suffix we have seen. So that prefix and suffix concept has to be utilized here. First we will see how the things are happening here. So prefix function for the pattern. Basically what you have to do now, we have to calculate a function called pi. This pi has to be utilized. How to calculate this pi? That algorithm will run. But before that, let us see the background, why pi is required. So basically if you see this diagram, you can see here that AB, BAC, BAB, this is there. This is the text, and the pattern is ABA, B, AC, A. This is the pattern. Okay. Now, in the naive algorithm, what is happening? You will match bit by bit. Shift will happen. Okay. So basically, what is happening here? You see. Consider the operation. So prefix function pi. First of all of us know what is prefix, what is suffix. So here we will try to find what is the longest common prefix and as well as suffix. That concept you will be utilizing here. Longest common prefix and longest common suffix. Common suffix and common prefix, that to longest one, that things you have to calculate. So prefix function pi for a pattern encapsulate knowledge about how the pattern matches against shifts of itself. That means we have to see the pattern itself, how the pattern is behaving. We can take advantage of this information to avoid testing useless shift in the naive pattern matching algorithm, and so avoid pre-computing the full transition function sigma. This is not required. Just try to understand that that function, prefix function pi, has to be calculated. Okay. Consider the operations of the naive string matching in figure 32.10a. That means this one, this they are asking us to consider. This is the text, full text, and this is the pattern. What it says? Pattern this against a text is. So for example, q equal to 5, small q, of the characters have matched successfully, but 6 pattern characters fails to. So here is a, you see, q equal to 5, or the characters are matched successfully. What they're trying to say that this is my pattern, A is matching with A, B is matching with B, and here it has stopped. And thereafter you can see that A is not matching with C. So mismatch happens. And if you, from the 0th shift, there is no match because B is not matching with A. First shift also not matching. First shift is matching, but then second character is not matching. So like that it has come, but at, let's say, shift S, we don't know what is the shift, maybe 0, 1, 2, 3. Shift number 3, you can see maximum number of matches happens. And that matching A, B, A is nothing but a prefix of pattern P. So that's what it says, that when Q equal to 5, that means 1, 2, 3, 4, 5, Q equal to 5 of the characters have matched successfully, but 6th pattern character fails to match the corresponding text character. That means A is not matching with C. So that is what they're saying. 6th position is not matching the information, but this much has matched ABA, BA. Whether you can use this information for our further computation or not. That is what, and that information will be stored in function pi. So you can see, knowing that this Q text character allows us to determine immediately the certain shifts are invalid. In the example for figure, the shift S plus 1 is necessarily invalid because this is S, and then when another move happens here, let's say A comes here, again mismatch happens. That's what it says, that S plus 1 is totally invalid since the first pattern character A would have been aligned with the text character. That you know. So, but however, the shift S dash, which is S plus 2, shown in the part B, which is this S plus 2. So basically here one prefix, we cannot call it prefix, prefix of the pattern P has matched with the text. At shift S dash, which is equal to S plus 2, here also some prefix of pattern P has matched. So whether you can use this information, so this time it is 5, next time it is 5, and we are calling it small q, and here also ABA is matching and we are calling it small k. Okay, so, and there is a relationship between Q, please sir, there is a relationship between Q and K. PQ is this, AB, which is PQ, which is, okay, this is also prefix, and ABA, which is this one, this is a suffix of PQ. The suffix of PQ, that is their ABA. So ABA also is a match. Okay, so this information we have to, if you can store somewhere in pi function, and if you can use that, whether it is useful or not, that is the algorithm, Knuth-Morris-Pratt algorithm. Okay, so what happens, we pre-compute the necessary information by comparing the pattern against itself. Now it is important to look at the pattern itself, which is nothing but capital P, and let us calculate the pi function. Okay, so here you see here, okay, this pi function has to be calculated. So this is so first we have two algorithms. One is, main algorithm is KMP matcher, which is using this pre-compute function P, which is nothing but pi only. This you have to calculate. This function is used by KMP matcher. That means whenever you stuck here, let's say this is not matching, that time if we look at pi function, and if you can do something and you can reduce the number of comparisons and matching, that is the algorithm intention, KMP matcher. Now we will directly run this algorithm, compute prefix function. This function now we are going to run, all of us, and we will see how this prefix table is getting calculated. Okay, so let us first, this algorithm we can write, and I am writing it, same thing, ACA, correct. So first case, this is the length of the pattern, which is, what is the length? 7 is the length. You can write it here if possible, not possible here. Otherwise, we will write it in a different color. Okay. So initially our prefix function 𝝅1 equal to 0. 𝝅1 equal to, initially it is 0. So 𝝅1 equal to 0. So step number 1 we can write. Here is step number 5 here. So let's say first case 1, like that. Case 1 means just we will running the algorithm and checking case 1. Case 1, initially our k equal to 0. 𝝅1 equal to 0. This is our pi function. So 𝝅1 equal to 0 initially. Okay, 𝝅1 equal to 0. Now it enters line number 5. Line number 5 it goes q equal to, so value of q is nothing but, this is nothing but for loop, professor. So remember in standard algorithm we write pseudocode like this, q equal to 2. That means it is nothing but a for loop, and by default increment is 1, 2, 3, 4, 5, 6. It will go up to value of m is 7. So m equal to 7, that also you keep in mind because size of the pattern is 7. So here q equal to 2. So first case, while our k equal to 0, so initially this while thing will be false. Yes or no? Because k equal to 0, 0 greater than 0, and then this is not at all possible. So this is false. So this thing you have to know if you want to learn algorithm in depth, like how this, so the alignment you have to see every time. So this while loop is actually ending here. Then this if is starting from line number 8. That means this if is independent of the while loop. Once while loop is exhausted, it will come to line number 8. So here it checks p of k plus 1. K value is 0, 0 plus 1 equal to p of q. What is the q value? 2. So it checks pattern 1, that means this A, pattern 1 is A, and with pattern 2. Pattern 2, q value is 2. So this 2 is checking. Whether A is equal to B? No. So first of all, this is the false automatically, but this is also not true. This is also not true. That means once this is not possible because 0 cannot be equal to 0. So this is false. Now it will come line number 8. P of 1 equal to pk. That p of 1 is A, which is not equal to 2, which is false. So this if loop also not work. So pi of q, line number 9 and line number 10. Pi of q, that means q value is 2. Pi of q is nothing but k. K value is 0. That means pi of 2 you have to put here 0. Clear? Next what will happen? Case 2, let's say. Now k value is how much, professor? K value is still 0. Nothing has happened with k. Nothing, no increment, nothing happens. K is still 0. But this for loop, q equal to 0, so q will become 3. Yes or no? So here q become 3. So if q becomes 3, so this while loop will be executed. What is the value of k? K is still 0. So this cannot enter, k greater than 0, so it will come here. So p of 0 plus 1, again 1, equal to p of 2, because now my q value is 3. P of 3, that means p of 1, A is equal to 3, that means A is equal to A. True, no? This is true. A 1, 2, 3, which is true. So that means if it is true, that means this line number 8 is true, then k will be incremented by k plus 1, that means 0 plus 1 equal to 1, it will be incremented. Okay, it will be incremented. And then that's all. This is not a loop. So it will come line number 10. Pi of 3 equal to 1. K value is incremented by 1. Pi of 3 equal to 1. Okay. So case 3. Case 3, what is happening? Now our k value is 1, q value 4. Yeah. So here, if it is the case, so it will enter, because now this line number 6, while k equal to 1 is greater than 0, which is true. This line number 6 I am talking about. Professor, correct? And p of k plus 1, which is nothing but 1 plus 1, 2, is not equal to p of q value is 4. P of 2, that means this one, b is not equal to 4. B is not equal to 4, which is not true. False, right? B is equal to 4. Correct, no? So if it is not, that means 6, 7 gone. 6, 7 is not executing. It will come line number 8. Line number 8 is p of 2 Because k value is still 1, P of 2 equal to one second. No, P of k, P of 2 is equal to P of 4, right?
They are not equal to.
They are equal to, right? So if not,
not equal to. Also case also not equal.
One second. So this 2 is 2 and 4, they are equal or not equal? So this thing is false. If this thing is false, means line number 7 won't be executed at all. It will go. So not equal to is there. Not equal to true means it would have come inside. Okay. So now P of, I'm lost. Line number 8, P of 2 equal to P of 4, right? Which is true. If it is true, then line number 9 will execute, which is nothing but k equal to 2 plus 1 equal to 3. So my k value is how much here? 2. K equal to 2. Q equal to 5. Let us come here. This line. So k equal to 2 greater than 0 and P of 2 plus 1, 3 not equal to P of 5. That means P3 A is not equal to 5, which is false. So this is false. It will come line number 8. P of k value is 2, 2 plus 1, which is nothing but 3. P3, so k value is 2 here, 2 plus 1, 3 equal to P of, my Q is still 5. Correct? So either P3 equal to P5, P3 equal to, which is true. Then k will become, k is 2, 2 plus 1 equal to 3, k will become 3. So my P5 will become 3. P5 is 3 here. Correct? Now case number 5 I will run. Case 5. So k value is how much? K is 3. So k is equal to 3. Q becomes, here 5 it is 6. Q becomes 6. Now come inside, 3 is greater than 0. And P of 3 plus 1, which is nothing but 4. P4 is not equal to P of 6. P4 is B. P of 6 is C, which is true. Then K will be equal to pi of PQ. QQ is 6. Q6 value, no, sorry. K, P, 3. K value is 3, no. So this is pi 3. Pi 3 become K. So pi 3 value is 1. K becomes 1 here. Okay. If K becomes 1, then definitely pi of Q is nothing but 6. Q6 become 1. So Q6 is become 1 only, it is coming. Check here. What is happening here? My K becomes 1 here. Yes, true. So in this case, it will, because it is loop, it will again come here. Line number 6. This is one time this loop is actually executing. K equal to 2, K equal to 1. When K has become 1, so 1 is greater than 0, and then P of, not P of 4, K plus 1, P2 equal to P of 6. P2 is B, not equal to P of 6, which is true. Then pi of, what is the K value? 1. Pi of 1, now pi of 1, pi of K equal to
0.
Pi of 1, which is equal to 0. Now, as such said, it is correct only you said, so now it becomes 0. Okay. Now, I have the, what is the K value? K7. K equal to 0. Correct, no? K equal to 0.
Then Q is equal to 6. We are completed while now we are checking if loop. If loop it fails.
Now how much K? K is how much?
K equal to 0.
K equal to 0. Q equal to 7, right? Q equal to 6, Q equal to 7. So now, so this is totally false. It will come P of, line number 8 will be executing P of 0 plus 1, P1, which is not equal to P of Q. Q value is 7. P of 1 is equal to P of 7, yes. True. So K will be incremented by 1, 0 plus 1, 1. So then it is done, that's all. Pi of, what is this? Pi of K, that means pi of Q, which is nothing, pi of 7. What is finite automata? Because our topic is string matching with finite automata. So those who are dealing with mathematics, you might be knowing finite automata is a technique, or you can call, what do you call it? Formal language and automata theory. This is a subject in computer science fully dedicated to finite automata, and then push down automata. These are all normally in terms of terminology they are called machines. Machine in the sense like how the codes are getting executed. When you write a C code or C++ code, how the syntaxes are getting executed and compiled. So for that we have compiler for sure. We have C compiler, we have other compilers. So they used to check the codes and the syntax analysis happen. That is the first thing. Syntax analysis is very top level thing. But internally the logic has to be correct. So they will be using different structures. So finite automata is one of the basic automata machine you can call, which deals with regular language. Okay, so I am not going to language. There is no need of going to the language and discuss here, because this is a different theory subject. In computer science, you will be taking that subject later on. So formal language and automata theory. Automata is a machine. Basically, what happens? You have hierarchy. Actually, in computer science, you have a hierarchy. Just I am giving basics so that it will be a little bit idea. We have to use formal finite automata for string matching. So if you see the Chomsky hierarchy, which is a very popular hierarchy structure, because we write in programming language, we write complex, simple program to complex program. So basically, problems normally problems and language are synonymous. If I say problem is pi, corresponding language will be L. That means you can represent a problem in terms of language and vice versa. Okay. So if you, and then language is there, with the language you have machines. So finite automata is the most simplistic machine. Meaning is what? Let's say I am giving you a language L equal to a to the power n, where n is greater than equal to 0. If I ask you which of the strings are getting accepted by the machine, in this case it is finite automata machine, you will say that first it is in, because a to the power 0 is 1, which is nothing, then single a, then a, multiple of a's, right? Like that all will be accepted until unless n goes or whatever. So this is a very simplistic thing. So where you are getting this thing? In case of programming language, you might be encountering this kind of things, and they will be using this machine, finite automata machine, to evaluate the syntax. Okay, this is one thing. Then this is very lambda. You can call epsilon, nothing, null string, yes, null string. You can call epsilon also. This is first thing I am telling you. Just basic background I am saying. And then languages are getting complex because problems are also complex. Such kind of strings are very simplistic strings, which hardly happens in the programming language, right? So normally what happens in the stack, when you write C program itself, you have a braces, right? Curly braces. Every time this is opening braces, this is closing brace. So this two braces opening braces has to be equal. How? What do you think? Who supports this kind of activity? Which is the data structure? Stack is obviously because you push one stack, in the stack you push one open brace, and then finally one close brace encounter, you pop it. So if at the end of the day, end of the programming, your stack remains empty, you can very confidently say that matching there is. So compiler will say no syntax error in terms of braces I am talking. There will be any other things also. So this kind of thing, that this is also a to the power n, b to the power a, like that you can write. This stack thing in terms of braces you can write. If let's say my language is this, a to the power n, b to the power n, and then if I say a and b is nothing but open brace and curly brace, so this is nn, right? So this kind of language, which is little bit complex than this, the corresponding machine is PDA, push down automata. Okay, so first finite automata, then push down automata. After push down automata, we have languages getting very complex. It becomes something like this: a to the power n, b to the power n, c to the power n. So 3 times you have to check. That means number of, let's say 1 I am checking, 1 1 to the power n, 2 to the power n, 3 to the power n. So your machine also will be becoming complex. So in that case, you have Turing machine. So let us try to understand the machine point. So first is finite machine, finite automata, then push down automata, then Turing machine. Turing machine is a final call. Okay, Turing machine is a final call, and the language which is corresponding to the Turing machine is called recursively enumerable language. You can imagine this is a recursive language. So this is just the background. So finite automata is such. So finite automata, what are the parameters of finite automata? You can see that it will be having an accept state. Like in this case, if I write a to the power n, where n goes to 0, or you can also write n is greater than equal to 1. That means in the string you need at least one a, right? Correct? So at least one a is the input, means it will be processed. That means it will accept. If I give a, b, then at b it will be rejecting. Thing won't be processed. So this is finite automata. Okay. So in finite automata we have this thing, 5 tuples. These are called tuples. Tuples is what? This thing will be represented in terms of states, number of states. Okay, states. So these states are representing, why it is called finite state? Because number of state will be finite. It should not be infinite. Okay, finite state. So Q represent, your capital Q represent number of states, and this is finite set of input symbol. Let's say your input symbol is only having, in our case, let's say our string is only having combination of ABC. So sigma will be ABC. Always you remember, because it is a matter of state transition, you can call it state transition diagram. Initial state will be always Q0. Okay, so there should be something which it will start with. So that is called Q0, initial state. And when string is accepted, let's say string is accepted, that will be like double circle, and it will go final state. Okay, so this is final state. So initial state Q0, final state is F, and then let's say in Q0, if I give input A, it goes to Q1, state Q1. Okay, so in Q0, if I give input A, it goes to state Q1. So that mapping is nothing but, you call it sigma, right? Sigma, delta. This is delta. Okay, delta is a transition function. This is a transition function. That means delta function, if you apply delta function at state Q0, if you take input A, then it will go to Q1. That's all. And maybe here also you can have something. Let's say this is not the final state. From Q1, taking input B, it goes to Q2. Let's say this is final state. So in that case, you have to write in Q1, state Q1. If you input B, it will go to Q2. So delta function is a function which maps Q0. Current state is Q0. Input is A. I'm going state Q1. That's all. Okay, nothing to worry about it. So if you see the finite state machine, it is actually divided into two machines. One is deterministic finite machine, one is non-deterministic finite machine. We'll just see the definition, because in this in our case it is not required. What is the definition? Deterministic finite machine means, let's say I am in state Q0 with input A, I will only be going to Q1. I won't go in multiple places. Okay, from Q0, if I take input A, I will be only going to Q1, specific, very deterministic way. I will be going Q0 to Q1. Whereas in non-deterministic, anything and everything is allowed. Okay, that is non-deterministic. We are not going into that, but up to this much you should know that finite automata can be divided into two parts. One is deterministic finite machine, non-deterministic finite machine. NFA in short, non-deterministic finite machine. In short, DFA, deterministic finite machine. Clear? So this is the definition. Okay, this is not required here. Just I am telling you the definition. Okay. Now string matching algorithm, we'll see how this finite state machine or finite automata. When we say finite automata, we are not considering DFA, NFA, all these things. Don't keep that thing in mind. Simply we directly say. First we have to understand 2-3 things. First thing is that we have to very well understand what is prefix, just recap, and what is suffix. This already you have discussed, but again just discussion. Let's say my pattern is A, B, C, A, B, C. This is my pattern P. So every time we will see what is the longest suffix and longest prefix, that is matching, and what is the length of it. That will be, this concept we will be using in finite state machine. Okay, I mean in case of finite state machine implemented towards string matching algorithm, we have to use that. So let's say pattern is this. So what are the prefix A, B, A, B, C, and then A, B, C, A, and then A, B, C, A, B, and then finally A, B, C, A. And finally, if you say take C, that will be like a complete string will coming. We will not consider that. And then prefix is C, B, C. Okay, and then A, B, C, and C, A, B, C. One second. B, C, A, B, C, right? Transition. If there is, ABC is there, yeah, ABC is there, that means we will make the transition, we'll see, that means this ABC which is matching here, then we'll use, ABC, yeah, ABC, this one, not this one, ABC and ABC is matching. Just remember that length is 3, three length prefix and suffix is matching up. This concept you have to exploit in our state, when we will make the state transition for finite state machine towards string matching algorithm. This concept has to be exploited. So this is clear. Prefix and suffix maximum length we have to see. So let us start it. So let's say our that A, B, A, CA. This is our pattern, remember? And so whenever you see the pattern, immediately you have to draw. First we will target the pattern, okay? So pattern length is 1, 2, 3, 4, 5, 6, 7. Immediately you have to draw 7 states. You have to draw 7 states. So we'll see. First state is state 0. Let's say this we will name it 0th state. This second state is 1. Third state is 2. 3, 4. So here what you have to do? We have to start from the state initial. This is the start state, okay? And this is the pattern. So initial my input is 1. My input is A. So we will write like this. Here I will write at state 0 input. Now here your sigma is nothing but ABC. A, B and C. This is your sigma, which are the alphabet, okay? So ABC, sigma is your ABC. Now what happens? We have to see at state 0, input is A, because first input is A. Every time you have to find if input A comes, input B comes, input C comes, what are the scenarios? Whether state transition will happen or not. If state transition happen, then the prefix and suffix maximum length, common prefix and suffix you have to find. So at state 0 you have A only. So if A comes it will be accepted because A is there in the input string. Okay, first we will deal with the pattern, then we will go to the text. Now don't think about the text, okay? So if A comes, put here A, fine. If A comes at state 0, this is first thing. Second, case 1. If B comes at state 0, then what happens? If B comes no match. So basically you have, so now here that concept will be applied. So let's say B only one character comes, so prefix suffix there is no things like only one character what. So there is no match, no transition, okay? B comes no at state 0, if B comes, it cannot go anywhere, right? C comes also, it cannot go anywhere. Because we are talking about state 0, initial state. C also comes, then no transition, nothing will happen. So this is case 1 done. Case 2, we are in state 1. Let's say if B comes, my first input is A. So B comes, it is not going to accept. Let's say in the second scenario, we will see if B comes, then at least 2 characters we need to find the prefix and suffix. So here is no chance, but already A is accepted. A is going to 1, state 1. This input is A, so it is going to state 1, okay? Now B comes in 0, it is not accepted first of all because first input is A. So cancel. C comes, that is also cancel, initial state. Second case at state 0, if in state 1, let's say A comes first. State 1 A comes because second input is B. If A comes, then what will happen? My prefix and suffix wala funda you have to use. So basically A, that means A, B, A then B, B comes, sorry, A, correct now, A. So AA means you have to find prefix and suffix both. So prefix and suffix both. So AA prefix is A, suffix also A, correct now? Prefix is A, suffix also. So what is the match? One character matching, right? So length 1. That means at position 1, you just have a self loop A1 because this is 1. At 1 itself, this A will come back. Okay? Correct? Clear? Let's say, so here what I say, after A, if A comes, it is AA. It should be AA like that, right? Now this is my string which is having 2 characters. So here 2 characters, as I said, whenever you have to check the prefix and suffix both. So prefix of A is A, and then A to you won't take. Suffix also A. So matching is there, AA matching. Length is 1 match. So 1 match means in state 1 you have to put a self loop and then A. Okay. Now if B comes here in state 1, let's say B comes at state 1, what will happen? So I will be having A. Correct, professor? Yes or no? So AB not matching, prefix is A, suffix is B, not matching, no need of any transactions. At 3, if C comes, then what will happen? A, C, nothing happens. Sir, thank you. Thank you. So whenever you have match, you just don't go to prefix. Because if state 1, B comes, as sir mentioned, B comes, it is directly going to state 2. Okay? If B comes, directly going to state 2. This is wrongly done because directly match is there, no problem. Now let's say if at A comes, self loop happens. If C comes, then it is S means suffix. No match, no clear. Doubt clear. If match is there means immediately you have to go to the next state. So at state 2 you are now, this is done. Okay.
So
Match means you have to immediately move to the next state. Mismatch happens, then only we will be seeing prefix and suffix. So next is case 3. Let's say we are doing it here itself, no problem. Case 3. We are in at state 2. Let's say if A comes, so this is done, this is also done. Let's say A comes, so we won't see anything, we will directly go to state 3. If A comes, directly go to state 3 only, no problem. We have just gone from here. Correct, professor? Then this is 1, this is 2. If B comes at state 3, at state 2, not 3, state 2, then what is my string? A, B, it should be ABB, correct? So now we have to find prefix and suffix both. So prefix of it is A, AB, suffix of it is B, BB. Anything is matches? No, so no need of transition for B. Just stop there. For B, you don't do anything. Point number 3, if C comes, then let's say at position 2, C at location 2, C comes. Okay, C comes. So my string will be A, B, C. Should have been A, B, C. So here, what is the prefix? A, B, suffix C, B, C. Nothing matches. No problem. Okay. So 2 we are only having input and going to state 3.
Yeah,
we are having a. So at 2, if A comes, directly it goes to state 3, right? No question asked, because after B, A comes directly. Now my concern is whether C and A, if C and B comes. So B comes means my string would have been A, B, B. So what is the prefix? A, B. What is the suffix? B, B, B. Not matching, no transition. If C comes, A, B, C. A, B is the prefix. C, B, C is the suffix. No match, nothing, no transition. Don't go out. At state 3, this is case 1, case 2, case 3, right? Case 3? Case 4. Very good, thank you. At state 3, that means I have done A, I have done B, I have done A. Now at state 3, if B comes, directly we will accept it B, no problem. If C comes, A comes, what is my string? A, B, A, A. It would have been this. What is prefix? What is suffix you have to find? A, B, A. What is suffix? A, B, A. Right? Is there any match? Yes. This is the match. What is the length of the match? 1. So from at state 3, you have to you don't have to think anything. You have to just go to state 1 with the input A. Correct? with the input that this is done. Now if C comes,
So another match is also there.
one second, huh?
ABA is the
ABA, but this is AAB, na? This is BAA, this is no match, right? Okay. So next is if C comes, then my string would have been A, B, A, C. What is the prefix? What is the suffix? Prefix is A, AB, ABA. Suffix is C, AC. No chance of match. So no need of any transaction done. So case 5 I am going to write. Case 5. So I am in state 4. So this B also has been done. Now I am here. My control is in here, A. So if at 4th state, if A comes, case 1, then immediately it will be accepted. No problem. If A comes, done. If B comes, what is my string? A, B, A, B, B. Now you have to find prefix and suffix both. Find prefix A, AB, ABA, AB, AB, B, BB, ABB, BA, BB. Any match is there? No match. Comes. Then A, B, A, AB, AB, C. That means prefix and suffix. A. Sir, wait, sir. C, B, C, A, B, C. B, C. Okay, at state 4 only A accepted. So we'll just delete it. So B and C are not accepted because no transition happens. So this is at 4, state 4. Case 6 at state 5. Let's say at state 5. So A has done. So this is we are here, right? So let's say at state 5, C comes. C comes immediately. We go to state 6. Yes or no? If B comes, so our string becomes A, B, A, B, A, B. So my prefix are A, A, B, A, B, A, A, B, A, B, A. Suffix B, A, B, B, A, B, A, B, A, B, B, A, B, A, B. So here we have a match here, A, B. Any other match? This one, right? A, B, A, B, A, B, A. A, B, A, B, A. A, B, A, A, B, A, B, A, correct? A, B, A, A, B, A, B. A, B, A, B, A. So A, B, A, B is matching. So in the two matches we have, we will take the maximum one. Length is 4. So from 5 we have to go to 4. With which input? B. Okay. What about with A input? Let's say if I rub this one. If A comes, then it becomes A, B, A, B, A, A. The prefix is A, A, B, A, B, A, B, A, A, B, A, B, A, B, A, B, A. Suffix A A B A B A B A B A. So here one match, correct? The length 1, that means from 5 we'll go to 1 with the input A. Okay, done. Next we'll go to the, so here A is done. Acha, what about C? C already done. C, no, C is there in, C is already input, B not matching, B also matching, A also matching. So done. For 5 state you are done. C is done. Now case 7. One second, you just write it, then I. Shall I rub? Case 6. Case 6. Huh? A is not matching, but prefix and suffix maximum length is 1. So we will go to state 1. And in this case, maximum length is 4. So we will go to state 4 for B. So shall I go to the case 7? Case 7. So this is okay, done. 5C. So now at 6. That means state 6. State 6 also. State 6 also. If A comes, what will happen? Because this A is there. So state 6, if A comes, then you reach to the final state, I suppose, because this is the last one. So final state, double circle. Say this input is A, final state, done. Case 2, I mean the second one is if B comes, then my string is A, B, A, C, B, let's say. What is the prefix? A, B. Prefix remains same almost. A, B, A, and then A, C, and then that's all. And then suffix is B, C, B. Any match is there? A, C, B, B, A, C, B, A, B, A, C, B. B, A, C. Any match? No match, no transition. What about the third one? If C comes, so C comes means my things will be like just instead of B will be here C. So this is C. Yeah, so everything will remain same only.
No, C.
No, in this case, so one second. One second, but the suffix, this one will change. This suffix will change. Instead of B, I am having C. One second. So here C, CC, ACC, BACC, ABACC. No match, no transition. So that is fine. We are okay with the transition. Now let's see what is exactly happening here. So this diagram, all of you have.
And it becomes ACB, right?
At sixth location, anything? No, I think correct only. Okay, in 7th location, if A comes, what happens? Directly it is going. No, in 6th location, 6th state. No transition. 7
This
step.
is separate. This is
Okay. So we'll see here is correct only. I suppose any transition is required from the final state. No, I guess from state 6. State 6. No, I think that table pattern you check. So basically, what is happening here? So shall I write the pattern here? What exactly we got? Our pattern is one second. The pattern is you see here at delta function, as I said, transition function. So at state 0, this is state 0, initial state. State 0, if A comes, it goes to state 1. Okay? And then at state 0, if B comes, it goes nowhere. At state 0, if C comes, it goes nowhere. Transition function, this one, let's say. State 1, you are in state 1 now. Only one is here, only one successful match is this A. State 1. So at state 1, if A comes, if A comes, it goes to 1. Help loop, just check your figure. If state 1, B comes, it goes to state 2, transition function. State 1, C comes, it goes nowhere, 0. Okay. So here if you see only one transition happen, two transition happen successfully, string A and B. C is not there. So like that, here at state 2, here state 2 is a new state. We have gone to state 2 new state, because if you see here, we have gone first state 0 to state 1, then state 1 to state 2. So in state 2, if you take A, state 2, if you take A, you go to state 3. Here also you can say state 2. If you take A, you go to state 3. State 2, if you take B and C, both will be 0, 0. Like that you go. So state 6, state 6, if you take like that, if you complete all these functions, only the shaded, here it is written, see the corresponding transition function delta and the pattern string this, the entire delta correspond to successful matches between pattern and the input character are shown shaded. That means only this shaded states only, and the inputs only successfully executed. Remaining all are false. Okay, remaining all are false. So basically what is happening? So let's say my text is text. So state 7, if you take B, it goes to state 2. State 7, if you take B, it goes to state 2. This is state 7. In state 7, if you take B, state 7, if you take A, it goes to state 1. Thing can come, no? It has to force that transition to the initial state, otherwise it will create problem. So state, this is 8, let's say. So basically A, B, A, C, A, and then if A comes further, this is state 7. So what are the prefixes? What are the match? You see only A will match. This A will come prefix. This A also comes suffix, no? Correct, right? Remaining also one state is matching, so it will go to 1. State 1. This we missed out. So if you see this, state 7, if A comes, this goes to 1. Not only that, if B comes, let's say this is not A, this is B. So what will happen? AB will be matching. AB and AB will be in case of suffix. AB will, so what is the length? 2. So from here it will go to
2.
This is the final diagram. So this is the final table. Okay? This is the final table. Now we will see if the text is something ABA. Text here. So AB, A, BA, C, A, B, A. This is my text. My pattern is Just now the pattern that we said, let's be ACA. Okay, this is my pattern. Now you do one thing in the text, you just make numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters are there in the text. Okay, so if you see the algorithm here, this one, so just now this state we have seen, no? So state Q0, in Q0 if A comes, it goes to which state? Q1 or 1. Okay, so like that. But here mismatch is there, so it will check whether the string that you have processed, because it will go 1 to n. In this case, n is 11. 1. Now these transitions are happening. So first this transition happens, this is also match, but at the end here mismatch happens. Where? Here mismatch happens. So this won't working. So what is exactly happening? You see at this location, this is okay. You can okay. So here you have match A B A B A C A. One match is there. A B A C A match is there. And so here you can see match is there. Once this is matching. Okay. Which, so here if you see the text length, it has gone up. No, at 9th location match is there. So this is 9th location match is there. I is 9, M is 7, 9 minus 7 is 2. That means if you consider this as a shift 0, 1, 2, at second shift we have a match. This is all about string matching algorithm using finite automata.